And the next talk is titled WonderLens and will be presented by Rong-Hao, Liang.
Okay, thanks for the chair's introduction. I'm Rong-Hao from National Taiwan University. And today we're glad to talk about WonderLens, a system of optical lenses and mirrors for temporary interactions on printed paper. Display devices become more and more portable and even cheaper with lower power consumption. Even so, paper still plays an important role today because paper is more comfortable to see and play with than electronic display. Also, paper affords natural interactions because we already know how to use paper. However, paper has its limitation. The content printed on paper is not interactive. When we interact with the printed content, the content does not change its state, so the interaction stops here. To add interactivity on paper, many research augment a visual display for users, such as holding a display or wearing a head-mount display, mounting a projector camera module to augment the paper, or making projector camera modules graspable. These methods are effective to provide dynamic visual feedback. However, this external device may be bulky or may introduce additional latency to reduce the immersion of interactions. To increase immersion, designers hide the sensing mechanism behind the paper and use audio feedback instead, such as placing an RFID sensor behind paper with voice feedback, or placing an EMR sensor behind paper with voice feedback. However, the modality of interaction is limited to auditory. Actually, adding a visual display on paper does not necessarily reduce immersion. For example, the magnifying glass helps us to see the printed contents in details, provide very immersive user experiences. When we move the magnifying glass, it feeds the enlarged content back to us immediately. So we feel this tool is useful. Optical lenses and mirrors are likely to have this property. Therefore, we explore the use of lens and mirrors by molding accurately and PDMS. By the way, PDMS is the material of making disposable contact lens. So, after analyzing the affordance and optical illusions, we identify a set of 5 basic lenses and mirrors to be the most useful. Tilted cylindrical lens. Rotating it on the circular symbol results in visual illusion of rotation because of optical refraction. Flexible convex lens not only allows for magnifying content by lifting it, but also allows for changing the magnification ratio by pressing it. Concave lens allows user to change the shrinkage ratio by lifting it. Prism, the beam splitter, allows user to break a line by rotating it, or connect the lines by moving it. Angle mirror is similar to a kaleidoscope. Moving it can proportionally scale a pattern, generate several replicates, or freely scales a pattern. The lens and mirrors provide immediate visual and haptic feedback, close the interaction loop, and therefore allow for more interaction design to be presented on a printed paper. But to facilitate human-computer interaction, such as guiding a multi-step process, the system should allow for communicating dynamic information. If so, the computer should sense user's operation as input and display the output accordingly. On the input side, to get a lens and mirror sense, we choose to add magnets on the lens and mirrors because the magnets are small and the invisible magnetic field can be tracked on and above the paper. Each magnetic unit is designed in unique pattern, so the magnetic field can represent their ID and states. To sense the magnetic lens and mirrors, we use GaussSense, the thin-form analog Hall sensor grid, as a sensing platform. The GaussSense senses multiple magnetic lenses and mirrors through the paper. For detecting paper, We mount an additional RFID reader and 2 small magnets on the sensing platform. Each piece of paper is attached with an RFID tag with 2 magnets. When a piece of paper snaps to the platform recognizes the RFID tag and loads the content for interactions. The magnets align the coordinates between paper and the Gauss sense. After sensor operation, the system can provide additional output in different levels of embodiment, and we show 3 examples to illustrate them. First, output with only audio feedback. In storytelling, when the user rolls the character's eyes, and the character vocally tells the user what he sees. And when the 2 characters look at each other, they chat. Okay. Second, output with a nearby point light. So in a CPR learning program, a user uses an LED-mounted flexible convex lenses as a stethoscope. When placing the stethoscope on the patient's heart, the user sees the point light change and hears the heartbeat. And then the user presses and releases the soft convex lens at a constant rate to save the patient. So the blinking light shows it's well done. By the way, the LED-mounted convex lens can be made wirelessly with BLE module and battery. Third, output with ambient light and remote display. In the hide-and-seek game, a user sets the time of the game by placing an angle mirror, and the ambient light and the remote display change at the same time. Then the user uses a magnifying glass to find out the character. When the character is found, the glowing lens prompts the user to check the remote display to see who is found and what the character is doing.
Goodbye.
Okay. So, conclusion, we introduced WonderLens, a system of lens and mirror that augment tangible and embodied interactions with printed paper. The double interaction loop allows for communicating dynamic information. Future work can consider using advanced methods of lens fabrication and visual designs or incorporating energy harvesting mechanism with paper. This project, WonderLens, shows another application of Gauss sense, which is enabling tangible interactions on printing paper. For makers and researchers who want to try out Gauss sense technology, we're happy to announce that the $19 Gauss sense is coming soon. Yeah. Thank you. Okay. So we have worked very hard on it. I'm really excited to see this finally happen. So if you are interested in this, please subscribe us on gausstoys.com so we can keep you in the loop. So thank you for your attention. I'm happy to take over question. Thank you. Okay, a large view angle is actually an important criteria for us to pick the lens. Actually, our lenses accept for a wide range of visible angles, so many people can see the same visual effect at the same time. Thank you.
Okay, then let's thank the speaker again.